outside the book kind of less. There'll be several times, like the hyperbolic, where I went outside the book. This is not in the Saxon book. It should be. It's in every other calculus book I've ever seen. And I don't want you to be at a disadvantage. So the general heading is numerical integration. Really, there are three integration methods that are really used. Left hand, right hand are used to introduce the fundamental theorem of calculus. So they're useful, but in terms of actually, if you had something you couldn't integrate, you wouldn't use left hand or right hand. You would use trapezoid to midpoint or preferably Simpsons. And I would like you to see all the strengths and weaknesses of each, all right? So there are three real main integration techniques or estimations. They're all used to say, I can't integrate this, all I can do is approximate it with some kind of area calculation. It goes like this. If trapezoid error was done two ways, I'd like you to understand trapezoid error in two kind of fashions. Say I did this region with two trapezoids. Here is one trapezoid, and there is another. Now, because those areas under those trapezoids is not the same, I would have error. I'll call this error 1. And that's error 2. And because the curve is concave. So far, so good?
So far, so good.
All right. Now, it is fairly common, however, to think of trapezoids as rectangles. Now, I don't know if you've ever thought of a trapezoid this way, but wouldn't you say that there's got to be some rectangle in between here where the area of that orange rectangle is the same as that trapezoid?
Yeah.
That's true. And the base of this is the average of the two trapezoid bases. So if you were to average the bases, then multiply by the height, well, that's one of the ways that area of the trapezoid comes from. It's that idea, averaging the bases, treating it like rectangle. Right? Now, if you were to, yes? Oh. Okay. Now, if you were to do this in that fashion, now here, I know that, in fact, maybe I should have done, I wish I kind of would have done, well, I think that's okay. Okay? If I were to do this in that way here, I wish I should have done one. Can you, sorry to make you mad, but can you dump this? I don't know why I did two. Can you do one trapezoid, please? I'm sorry.
It's all good.
I'm not sure. I don't. There's no point in doing two. I can do the same. Now, wouldn't you say then that this trapezoid, here's base 1, and here is base 2? Okay? And I know it feels like triangle, but think of it like a trapezoid. Base 1 plus base 2 times the height divided by 2. Are you with me? All right, now, let's do this averaging idea here. If I were to take that trapezoid, instead of looking at it like this, look at it like this, and then think, well, isn't this just the average of the two y values? In other words, I could think of this like some kind of average y. Now, the y's go from 0 to, this is a cube you'll find, so 64.
So as far as the halfway point between the two, it would be somewhere in here like 32. Now what I'm suggesting is that you pretend like this is a average base times the height, where the average base here is the starting f value, f at 0 plus f, f at 4, yeah, I guess, I'll go there, divided by 2. You with me? No, you don't, you're not with me. Okay. Let's go back and try this again. Sorry. Okay.
And it shows when you started putting out the graph.
Gotcha. Okay. So, let me write this a little cleaner here. Okay. Oh, okay. I heard it. Oh, all of a sudden it went good. And to think of this as, let's just call this f at 0 plus f at 4. Aren't those the bases, right? Base 1 is f at 0. Base 2 is f at 4 times 4 divided by 2, all right? Now, if I were to, rather than thinking of that as a trapezoid, let's instead think of this as an average f value that's halfway between the two. Well, because that is what I'm doing. I mean, I'm adding two y values, dividing by 2. Now, the average y value between the two would be right in the middle, between the max values and the min value, okay? That's the average y value. Now, if I were to take that and multiply it by 4, these areas should be that blue trapezoid there and this blue rectangle here. They should have the same area. Same area. Okay. Now, if those have the same area, then they should also have the same net area. Now, if I were to look at this, call this error 1. Now, wouldn't you agree that in this first region here, that rectangle is overestimating the true area? Yeah. Okay? This error 2 is below the true area under the curve, right? So when I say their errors are equal, this, I'll call it this general error over here, is equal to the difference between those two errors. If I took the overestimate, take away the underestimate, they'd be equivalent. Okay?
Wait,
So if I were to take this area and take it away from this little region here, what's left would equal that area.
okay, so like that box, there, you won the whole box, like that.
Right. It's a net area.
Not the whole area.
No.
You gotta include that top part too.
Exactly. You have to take that away. So this overestimating error, take away the underestimating error would be net error, and that net error should be the same as that net error. Are you with me?
I believe it.
Okay. I'm going to say I'm not feeling super confident. I'm not sure I'm making this clear very well. Sorry. Now this idea of average heights, it can be used in a lot of trapezoid problems. So would you go to number 6 on the homework? Number 6. On the homework I just gave you,
G with the
it's white.
curvy graph.
Yeah, it should be that curvy graph. Yeah. All right. So let me explain how we could do this fairly quickly, okay? If we were to use or estimate the area under the curve of this with 8 trapezoids, I could do what's this base, times 1 divided by 2. And it's fine, and it would be a lot of calculating. But it would be a heck of a lot easier of, instead of saying, what's this base plus what's this base divided by 2, to take a stab at what's in between these two y values. So ballpark, between those two y values, it looks like between 0 and maybe 1.5-ish, maybe, what do you want to go with? 1.7, okay. Now that trapezoid then, 0.7, sorry, 0.7. Okay, 0.7, when I say that, then I'm saying let my first estimate be 0.7 high times 1y. Are you with me? Okay? Now that rectangle really represents a trapezoid where I average the two up. The next, halfway in between, it feels like halfway between maybe 1.5 and 1.9. What do you want to go with? 1.7, okay? That's halfway in between the next interval. Take a stab at what's halfway between the y values of the next interval. What do you want to say? 2. 2? Okay, 2. What's halfway between the next two y values? 2.6. I'm good. 2.6. What's halfway between the next two y values? Feels like it goes from about 3 to about 3.8, maybe? 3.4, okay. All right, the next one, it feels like maybe between 3.8 and 4, so 3.9. The next region looks like from 4 down to maybe 4.1, 4.2. I don't know. What do you think in the region between 8 and 9? What do you want to use for an average y value? 4.6. I'm down with 4.6. Okay. 3.6. Sorry, 3.6. Right. Okay. In the last region, there's some drop off. It looks like from around 3.2 to 0. 1.6, 1.5 sounds good. Okay. So as an estimate then, we're feeling like 2.4, 4.4, 7, 10.4, 14.3, 17, 18.3. I'm feeling like about 19.9. I don't know about you. What do you think? You're just going to take my word for it? Okay, 19.9. All right. The main idea, though, is averaging the two y values is equivalent to a trapezoid. You understand? All right. Now, the usual then question that people go through their heads is, isn't that the same as midpoint, that in between somewhere? And is it? Okay, it feels like it is, and there is some over-under like midpoint, but in these trapezoids, I'm using the point that's perfectly halfway between the y values. And midpoint, you're using the point that's perfectly half between the x values. And so it is not the same, it's a little different. So if I were to look at, say, this curve here again, when I did this trapezoid, I draw the height at the average of the endpoint y's, as we talked about. So my y's went from a y of 0 at the left side to a y of 64 at the right, so our average y is 32. So when I did this, again, remember that this area, the area under this, is the same as trapezoids. Same as if I did one trapezoid. I know it looks wacky. Obviously, it looks like a rectangle, but if I were to do the area of that trapezoid, it would have the same area as that rectangle. Understood? All right. Now, if you did midpoint, you would find that midpoint x value, which is 2, go up to the curve and draw the height there. Obviously, then that is very different, okay? This is the midpoint estimate. Now, in terms of error, which feels like it has more error versus less error?
I feel like the bottom one has, or the right one has more error. Midpoint has more error.
Midpoint has more error, because I told you yesterday trapezoids are better than mid. I lied to you. So, we'll talk about that in a second. Okay,
It's fine.
this curve is concave up. Do trapezoids over or underestimate the true error area?
When they're
When you do a trapezoid, go back to a picture of the trapezoid. Do trapezoids over or underestimate?
when it's concave up, it
It's overestimate because it's concave up. Trapezoids will overestimate. All right, now look at the midpoint. Will the midpoint overestimate or underestimate the area under the red? It'll be under, okay? Definitely this region where it's overestimating is far less than this region where it's underestimating. And so midpoints are definitely going to underestimate in this case, this concavity case. You with me? Okay, under. All right. Now, we could therefore find a bound for this. The true area under this curve could be bound on both sides. I know trapezoids overestimate, so they're the upper bound. I'll call it T. And the lower bound, midpoints underestimated, I'll call it M. Now that's actually a very narrow window, much better than you can do with left-hand, right-hand midpoints. All right? And it's, again, about the concavity. If F is concave up on the interval, then the interval or the area will always be less than the trapezoid and more than the midpoint. But if F is concave down, then the true area under the curve is more than the trapezoid, less than the midpoint. Right?
Is it always going to be like, is the midpoint always going to be larger than that? Because I feel like in some situations.
So yeah, this is generally speaking. If there's changes in concavity, then all bets are off. Yeah. Okay. Find the two estimates in the exact value. Now this is the cube graph. Y equals x cubed on 0 to 4. So would you find for me all three, the exact, the trapezoid, and the midpoint estimates? Using 2. It's pretty common. Most textbooks would abbreviate those M2 for midpoint, 2 rectangles, and T2 is 2 trapezoids.
Oh.
Use 2 trapezoids. I'm using 2 intervals where what x values would the midpoints be drawn? I break it into 2 intervals, 0 to 2, 2 to 4, so the midpoints are at x of 1 through. Are you getting 56 and 80 for your estimates?
Yeah.
You could have made a mistake.
I'm getting
Oh,
that.
no, I see.
becomes x to the third, it's cubed.
Well,
So
that's
it's not just like
true.
x to the, it's like it's like x at 2. Or y at x, x 2. That's 8, I don't know what that means.
How we doing? So excited. This is awesome. Okay, so what do you notice about the accuracy of the two methods? Which one was, first of all, do you agree it verifies our over-under estimate conclusions that midpoint was below the true and the trapezoids were above the true? Yes?
Oh my goodness.
Okay, what do you notice about which one's closer?
Midpoint's in this one.
How much error in the midpoint?
12. Or 8.
8. How much error in the trapezoid?
14.
Oh, wait.
24, God.
No,
No.
it's
16. So it seems like you could conclude that there's twice as much error in the trapezoids. Or you could say that midpoint is twice as accurate. Yeah?
Yeah.
Now, that's for this case. I chose this case. I mean, it's as pretty princess as it gets, okay? It's not always this. And that would not always be exactly the case, but it's a general rule of thumb. Now, let's talk about then, if you were a genius and you wanted the best possible estimate, then let's put those two ideas together. We know the true integral value is between the two methods. And because it's between the two methods, it would be logical to average. Average the two, exactly. Average the two. And get even less error. But we just said the midpoint method is generally twice as accurate. So not a straight up average, but a weighted average. And that is Simpson's rule.
In general, is midpoint 2 times length or?
A general rule of thumb, not exact.
Okay.
Okay? Now, if you were to do this in a weighted average case, then we're going to use Simpson's with 2 is equal to a weighted average of the two values. So if we were to do a weighted average, we would do what? 2 midpoints and trapezoid and divide by 3. Okay, weighted average, right? Now look at then the details of this. If I were to write this out a little different, it would be 1/3 times 2m plus t. Oh, that's cool. 1/3 times. Now, 2m would be something like 2 times the midpoints. They were 2 wide, and the heights were f at 1 and 3, right? Parentheses city. Plus the trapezoids were 2 over 2, 2 for the parallel, the x delta x height, which really is a base, the half of the formula, and then we did f at 0 plus 2 f at 2's plus a single f at 4, yeah? Let's clean this up a little here. 1/3 of, let's go with, yeah, I closed that, I didn't close that back correctly. 4 f at 1's plus 4 f at 3's plus f at 0 plus 2 f at 2's plus a single f at 4. Way down. That is true. Now we'll organize this from least to greatest. So this should be a single first, and that comes from the trapezoid. And I'd run into 4 f at 1's. So the next thing I'd get is 2 f at 2's plus 4 f at 3's plus
No, just
a single f at 4. Now that
follow.
That's Simpson's rule. The idea is that you have a third out front. Now that comes from the weighted average part of it. 2 midpoints plus 1 trapezoid. The delta x, that's pretty common. Obviously we need, it doesn't really show up in here because it got kind of lost in the mix, but delta x. Now the y's are the gotchas in here. The y pattern goes 1, 4, 2, 4, 2, and it alternates in here between 2 and 4s. Starting with 4 and then going 2. You'll always see it end at 4 and then end at a single. Simpson's rule only uses even subdivisions, okay? This, when you use, actually, let's go here. So if I were to label this with Simpson's rule, this is actually Simpson's rule, not with 2. I know we use 2 rectangles and 2 trapezoids, but it's actually 4 Simpson subdivisions, because if you include the points at which we did the midpoints and the points at which we did the trapezoids, we get 4 subdivisions, right? So this is going to pan out to be actually Simpson 4. That 4 Simpsons is always going to be twice as big as how many midpoint slash trapezoids, because we're collecting the 2 and doubling the amount. Because this is always double the amount of trapezoids, it'll always be even. It's always going to be doubling some original number of trapezoids in midpoint. So it'll always be even. The delta x is the same as always. It's just the total region divided in different chunks. And you're going to be starting the y values at the starting point plus some number of delta x's over. Let's get into an example.
Mr. Ring,
Yes,
what
question.
is the, like, S sub 4? Like, I don't get the 4 traps or that whole idea.
So that's f sub 4 is using Simpson's rule with 4 subdivisions.
Like, what were those 4 subdivisions?
4 subdivisions. So good question. The trapezoids, which I'll do in blue, were from 0 to 2 and 2 to 4.
Yes.
Okay? But I'm also doing midpoints. So midpoints I used 1 and 3. Now if I combine those 2 subdivisions, then I'm dividing every 0, 1, 2, 3, and 4. So altogether I get 4 subdivisions using both. And that actually shows up right here. You're using between 5 points, you get 4 regions. Does that make sense?
Mm-hmm.
Okay. Gotcha. So let's show how this looks. If you did this problem originally with Simpsons the whole time, then it would start by saying something like this. Delta x is the total region divided by 4 subdivisions. So delta x is 1, okay? By Simpson's rule then, I have 1/3 from the weighted average times the delta x of 1. And inside, I'm going to have y or f at 0. Now I'm going up by a delta x each time. Delta x is 1. So the next is 4 f at 1s. Then it goes down to 2. 2 f at 2s. Then it goes back up to 4. F at 3s. And then it ends at, when I get to the left end, the right end point rather, which is 4. And there's a single one of those. Understood? Okay. So I got 1/3 of 0 cubed. 0 plus 4 times 1 cubed plus 2 times 2 cubed, which is 16. Oh, yeah, I'm with you. You're one step ahead of me. 4 times 3 cubed is 4 times 27, and 4 times, or 4 cubed is 64. Okay, so I have 1/3 of, we got there 20 plus 108. So 128 plus 64 is 192. 192 divided by 3 is 64. How'd we do with the exact? It is exact. It is exact. That is exactly the area. Now then, Simpson's rule actually estimates cubes and below perfect. Is exactness. And why? William, welcome to that list. Okay? Yes, ma'am.
Okay, so it's exact, but you were drawing squiggly lines.
Yeah, well, I didn't want to ruin it ahead of time.
Okay, so like, can we
I
just
didn't want
write
to tell you it's going to be exact.
so we can just write equal sign?
Only if
Or
it's a cube or below.
approximations?
Only if it's a cube or below. Okay. So usually it's an approximation. In this case, it's a cube, and it works perfectly for cubes and parabolas. All right. Now, a couple of fun facts about Simpson's rule. First of all, I told you Simpson's rule finds the exact for cubes and parabolas. There is an error bound for Simpson's rule, and it actually uses up to the fourth derivative for the error bound. But this is so cool. This is my favorite part. This usually comes from weighted average, the idea of weighting your averages. But did you know that Simpson's rule is the same as if in this subinterval here, instead of using a trapezoid to estimate the area or a rectangle, if I did a parabola here and found the area under that parabola with basic calculus, and then I did a different parabola here based on choosing 1, 2, 3 points, finding an equation of the parabola, and doing the area under that. That's actually what Simpson's rule does. It finds estimation area of the curve using parabola. Okay, now, it's proving it from a total backdoor, totally different angle. It is amazing. All right. I'll let you think about that some other day.
Mr. Rickman?
Yes.
Like historically in relation to calculus, was this found out before or after like?
Oh, much after.
So like,
Not much after. After.
so they're like, we can just
Not one generation removed. And this, by the way, Simpson did not in any way, that's typical in most math. The guy it's named after is not the guy that came up. It's usually a guy that got shafted before, and he said, we gotta make it up to that guy, so we'll name this after you. That's pretty typical in math. It gets named after somebody that got shafted further.
So pretty much.
Kramer's rule is actually invented by Greg. All this stuff.
So pretty much this guy's like, he could have just differentiated and integrated it, but like.
But the point is you wouldn't use this for something that you couldn't.
Yeah.
Okay, so, believe it or not, this, if you know how to use this, I could find the log of 2 to 8 decimal places, just like that, with no calculus and no calculator. I could find pi to 8 decimal places, just like that, using this,
How?
no calculator.
Yeah, that doesn't make sense.
Yeah, let's see it.
You gotta see, all in good time. It's actually a little bit is on your homework. You'll see. Believe me. What is an integral that has pi or something pi-ish as an answer?
Wait, what's wrong with this?
Which integral has pi as an answer?
Circle would make sense. Think of this. What is that?
That is the like.
Oh, but it's not
What is it? Okay, so if you estimated this, if you found this, you will find
It's
5. Now, could you estimate the area of the curve using Simpson's rule?
Oh, you.
And that would be pretty easy calculations. I could put 1 over 1 plus a half squared, no problem. That's arithmetic. It would involve Simpson's rule and that, as many as I wanted, find it as exact as I want, just like that. All right. So that's proven. That's on your homework, and we'll talk about that later. Question. Oh, so the next thing, the test is tomorrow. It's supposed to be today. Oh, okay. I have a terrible feel for. I could have sworn that the majority said tomorrow.
Really?
But maybe it's just those people are loud. In retrospect, I shouldn't ask for hands, but it's done. It's why I was just right. It's
two angles. I don't even have this.
Is that one of those options?
Yes. The test is going to be 293, not 94. The review was made before he made that call, so the review has 94 on it, but you can not do it. You can not do the whole review. Because the test is 293 and it's not understood. Okay. I would normally review before school, and I will be happy to review before school, but I have to leave at about 7:15 tomorrow to set up the UNC competition. So if you want to review, I'll still be here from 6:45 on, but I have to leave at 7:15 tomorrow. Okay? All right. Now, to throw you a bone here, I have, for Halloween treats, we have cookies. But the lesson took so long that you don't really have time to decorate them like I wanted to.
Let's do it.
All right, whatever.
We can just decorate good. Or not go to 6,000.
Yeah.
So we can get a pass. Trust me, I get a pass every day.
I'm not going to pass which is less important.
No, you can't.
It's 3 out of 5 days a week. You are only the pass next year.
That's it. So twice my class, I will have 3 minutes late to hide that night. And counting cards. That is my biggest Alex. Are you feeling that? Oh, I probably do. That line got pretty big. I don't know why I can't. Hey Brady. Dude, how's it going for you? I'm making it good, sorry. Yeah, well, I love it. I'm getting faster. You keep on doing it too much, though. I got like so sick of it. Yeah, I heard something about spring. There you go.
You're welcome.
Let me get our folks up.
All right. Right, don't feel like this.
Just look at the star.
We both grow, and so it's about. Technique. There's a technique.
but you would have to use your, X goes to infinity. One eye.
Wow, that's.
From here, it looks like five. On a cookie?
Hey, Mike.
Famous Halloween cookie.
What is this, Mike?
Alright. So there goes the official in terms of doing running any math.
Happy Halloween.
Happy Halloween. Cookies over math, it's terrible, it's wrong.
That is Mr. Ray, he gave us a 30 question pop quiz.
On Halloween?
He was like, happy Halloween. It was yesterday.
Oh.
You know what you have to do? You just have to bring in snacks to that class and then ask Mr. Ray to hand it out. And it's
I don't want to have my backpack.
Class.
Sounds like.
yeah, but unless you bring in Kit Kats.
Yeah, I have my backpack somewhere in this world and it's not.
I brought in Kit Kats.
Alright.
Where's my backpack?
I don't
So it feels like nothing is due.
know.
Mr. Ray was
Now.
I don't know how else to use the backpack.
Alright.
Anybody see
over
Alex's
the course of
backpack?
like 8 years.
Oh, did I? Oh, sorry, I recorded us eating cookies.